Okay, we've got a worked example here, which is in the forces section, and this is a moments problem. A plank of 100 newtons. Let's just have a look at the problem. A uniform plank AB has weight 100 newtons and length 4 meters. The plank rests horizontally in equilibrium on two smooth supports, C and D, where AC equals X and CD equals 0.5, both those in meters. The magnitude of the reaction of the supports on the plank at C is 75 newtons. Modelling as a rigid rod, find the magnitude of the reaction of the supports on the plank at D. Okay, so first things first, let's get a nice clear diagram. As I keep saying, don't be tempted to scroll on this thing here. That's included in the question. Draw your own diagram. I've cheated a little bit, but by copying and pasting. But this is my diagram, and then able to mark my lengths and forces on here. So we've done that. Okay, so now the first thing with lots of these moments problems is that let's not forget the linear forces. We might get a bit carried away wanting to take moments about a point, but the linear forces might also be important, and so it is here in part 1, because if we look at this and linear forces here, then there is no acceleration in the vertical direction. In fact, the whole thing is in equilibrium. So the downward forces must equal the upward forces. We've called this reaction here at D R. So we've got R plus 75 equals 100, and therefore R equals 25. Okay, so that it's only 1 mark, but that is an important part of the question. And then the value of X, that's this length here. All right, so to do this, then we take moments about a point. We can pretty well always take moments about any point. We choose whether it's along the beam or whether it's some extension of the beam even, or even some point out in space, theoretically. But we usually want to take it from a point that simplifies, usually knocks one of the forces out there. So we can simplify by not having to consider one of the forces. That's not really a factor in this one, because we know all the forces involved, don't we? There's only 3. So we take moments about point A. But if you wanted to work this through and take moments about a different point, then that's you could give that a try. Moments about A. So the clockwise moments, we've got this 100 newtons acting from the middle, so it's therefore 2 meters from A. And the anti-clockwise moments, we've got the 75 acting at C, which is X meters from point A. That's part of the question, plus the 25 from this R acting at this distance. Well, that's X, and that's 0.5. So the whole thing from A to D is going to be X plus 0.5. It gives us a nice equation in X, and we can just work that through. And that gives us X equals 1.875 meters. So it's kind of most of the way to the center, isn't it? It's not far from the center. Okay, so that's parts 1 and 2. Let's just go on and have a look now at parts 3 and 4. Okay, what happens? A stone block, which is modelled as a particle, is now placed at the end of the plank at B, and the plank is on the point of tilting about D. Find the weight of the stone block. Now, again, if we've got this kind of situation where the model has changed and we've got the weight here, these reactions have changed here, then redraw the diagram. If you adapt the original diagram that you've drawn, then it could become a problem. If you need that diagram again, you might need to check, or you might need to go back and rework the first part of the question. And if you've got lots of other things marked on the diagram, it's going to get a bit confusing. So I would recommend that you redraw the diagram, and that's what I have done here. Okay, so what we've got is I've kind of marked in this particular distance. We know x, of course. Now I'll just put that in because it's a little bit more concise. So that is the distance there. Now we've still got the weight here. Now the key point though here is that because we're on the point of tilting, then the reaction at this support C is going to be 0. Okay, so you can imagine that actually all of the anti-clockwise moment is really being is going to be taken by this 100 newtons due to the weight, and all the clockwise is going to be taken by this W. So that's what happens there. I think you can envisage that's pretty well what is how it's going to work. You get the same sort of thing with if the plank was suspended by 2 ropes, for instance. A similar sort of thing, you would find that one rope becomes slack and there's no tension in it. Anyway, this is supports, so that is what we've got. So if the block is about to tilt about D, then the reaction at C equals 0. Now, the other thing is just looking at our vertical forces again. We've got R2 is going to be equal to 100 plus W. Now, to solve for W, then it would be sort of quite natural, I think, to take moments about somewhere other than B. You think, well, we want W in the equation, don't we? In actual fact, I mean, I've thought it's slightly easier to do it around B, because if we can find R2, then we sort of automatically found W because of this relationship here. So that's what I did in the first place. So we've got taking moments about B. So clockwise, we've got R2, and this length here, we know X, of course, is going to be given by this. So I think you just have, I'll not kind of go through the details of that, but you should be able to kind of work that through for yourself. Because we know X, that actually is 1.625 meters. And then the anti-clockwise, we've got 100 newtons acting 2 meters from B. Again, it's in the middle, isn't it? So we've got a nice equation in R2 there, which we can solve to give us 23.08 newtons to 2 decimal places. So if you're rounding, basically, you don't forget to put your accuracy in. Now, yeah, that's okay. But you might say, well, what happens if we take moments about D? Well, that is fine. It's a little bit more complicated. We've got to work out what this distance MD here is. This from the midpoint to there. So we've got to do a little bit of kind of algebra. It's slightly more complicated to work through, and I'll not go through the details, but you can pause and just satisfy yourself that that is the case. Again, we know what X is. So at this point, we can substitute our 1.875 in, and we get that distance is 0.375. So MD is 0.375 meters. Okay, so clockwise, we've got W acting at 1.625 meters. That's what this is once we've substituted our X in here. So I mean, I've abbreviated this slightly just to kind of fit it into a smaller space. If you're doing it in an exam, you might want to kind of do a little bit more calculation on these lengths. But that W is 1.625. Sorry, this distance of W from the point D is 1.625. And then in the anti-clockwise sense, we've got 100 newtons acting 0.375 meters. From the center. So an equation in W, might simply work that through, and of course it gives us the same answer, 23.08 newtons to 2 decimal places. Okay, so that is that. Part 4, explain the limitation of modeling the stone block as a particle. Well, in reality, it's it's going to be spread over a length here, and that's going to have an effect. It doesn't all actually act from one point, so it's not going to be exactly the figure that we're assuming, but we're modeling it, so it's a reasonable assumption to make. But yeah, it's not a particle. So the moments that it actually exerts here is not going to be quite as we've assumed. And then the Planck is a rigid rod. If it's not rigid, then there's going to be some bend in it, and so there'll be some torque. Once you bend the Planck, there's actually some torque involved in, to spring back into place. So that we're ignoring that. And of course, if it does bend, of course, then the distances from any fulcrum, any pivot about which we take moments, is actually not going to be quite the length of the bar of the Planck. So yeah, that's a simplifying assumption. Okay, so there we go. That is actually quite useful and a very typical kind of problem with for these moments problems. So hopefully you found that interesting, and yeah, a few pointers in there. First of all, don't forget your linear forces, and secondly, this point about when it's about to tilt, then likely is not one of your forces is going to go to zero. So yeah, so hopefully that's been useful, and thanks for listening.